So welcome back to the last talk of the day, of day one. Now we have Pratyush Mishra, who's going to be speaking about the Rust ecosystem for zkSNARKs. I know there's people who came just for this talk, so they're very excited to hear what you have to say, and so am I. Take it away.
Hi, everyone. Thanks, Anna, for having me. And I'm excited to get this talk. So in this talk, I'll be talking about arkworks, which is our Rust ecosystem for developing and programming with zkSNARKs. This is the joint effort of a lot of my excellent colleagues at Berkeley, as well as a lot of external contributors. The code is available at that link on the bottom. OK. So let's say you want to make a zkSNARK application, right? So maybe you want to make the next Zcash or the next dark forest or anything in between. To do this, you actually have to develop knowledge of a lot of domains. So not only do you have to figure out your own application, but you have to figure out things relating to SNARKs, such as finite field, elliptic curve, or polynomial arithmetic, information about your proof system, such as security properties, efficiency, so on. As well as you have to figure out how to express your problem in a language that the constraint system understands, that the SNARK understands, right? In a bit more detail, you need to have knowledge of many complex domains, right? So at the lowest level, you need to figure out how to optimize your arithmetic. Above that, you need to understand very non-trivial SNARK constructions, as well as the security properties they offer. Above that, you have to, as I said, express your problem in a language that the SNARK understands. This is called constraint system programming, right? And within this language, you have to implement securely your primitives, such as hash functions, PRFs, Merkle trees, and so on, right? And after you've done all this, you still have to reason about the properties of your possibly complex cryptographic protocol, right? So this is a lot of stuff to try to figure out when all you want to do is just to develop a simple SNARK application or SNARK-based application, right? And this is made worse by the fact that every few months there's some new techniques popping up, right? Your SNARK that you're using now might become completely outdated in 6 months down the line. All right, so how can we sort of control this complexity? How can we, simplify the job of people working with SNARK so that anybody can contribute? So let's try this tool that everybody loves. It's called abstraction. And let's zoom out from these 4 domains and try to abstract away some common properties that you want for each of the roles within the ecosystem, right? So if you're an application developer, right, all you care about is writing down your application, and maybe you have some interfacing with the constraint system to express your problem in a language the SNARK understands, but you don't really care about the proof system or anything, or curves and so on, right? If you're a SNARK developer, like you're developing new SNARKs or implementing them, then you care about interfacing with the constraint system because your SNARK understands some particular constraint system. And you care about interfacing with some elliptic curve or finite fields, but primarily you're focused on implementing your SNARK and making it efficient, right? And at the bottom level, you have your algebraic objects, such as fields and curves, and you have to optimize the arithmetic there, right? So in a little bit more detail, the things you care about at each level include, at the top level, are good performance. So you want your application to run quickly and not be slow. It's the minimum thing that you care about. But you also want it to be easy to read and easy to write. And part of this requires that writing constraints is ergonomic, right? It shouldn't be look unpenetrable or impenetrable to auditors or contributors, right? And at this level, as I said, you don't care about details about the kinds of SNARKs that you're using as long as it satisfies security properties, and you don't care about the kinds of curves that the SNARK might be using underneath. OK, that's the top level. At the next level, when you're developing SNARKs, here, again, you care about good performance because it affects the applications above you. But maybe a slightly non-obvious property is that you want your implementation to be high level. And in particular, you might want it to look similar to the math description. And what this allows is that an auditor or somebody else looking at the code can easily match it up with the description in the paper, right? And then they can gain some confidence that, oh, this implementation is actually possibly secure if the math is proven secure, right? And at this level, again, you don't care about what kinds of curves you have, as long as they satisfy the properties that you need, such as there being pairing friendly or there being a cycle. You don't care if it's a BN curve or a BLS12 curve. You just care about the pairing friendly property, for example. And you don't care about how constraints are generated, right? You just take in some constraints and the assigned witnesses, and you produce and you want to produce a proof. OK, so that's the SNARK development level. And what about for algebra? Here, you're implementing new fields and you're implementing new curves, right? So you want this task to be easy. You don't want to have to repeat the same code 100 times for 100 new fields, right? But you also want to ensure that the performance of this sort of easy implementation matches that of a hand-optimized implementation. You shouldn't have to sacrifice performance to get readable and easy to reason about code, right? And across the entire stack, you also care about other things such as memory safety and ease of auditability, ease of readability, and so on. Right? So these are common concerns. Okay, so the question is how do we achieve the separation? Because at the moment, unfortunately, many people working with SNARKs have to be experts in all three domains, right? So the question is, how do we separate the concerns for each of these domains? And our answer to this is to develop arkworks, which is a modular and coherent ecosystem for developing SNARKs and working with SNARKs that provides low-cost abstraction, so that you can abstract away your lower-level concerns without worrying about performance at all. Okay. So in a bit more detail, arkworks consists of a few libraries. At the lowest level, you have your libraries for your algebraic objects, such as fields, curves, and polynomials. And these provide a generic interface that can be reused by the next layer, which consists of concrete instantiations of the fields, as well as libraries for programming and specifying constraint systems. Okay, so that's your middle layer. And this layer provides a generic constraint system interface that can be used for developing gadgets. So for common objects such as hash functions, PRFs, Merkle trees, as well as finite field arithmetic, elliptic curve arithmetic, lots of common operations inside SNARKs. All of these are developed generically over the underlying constraint system API. And we also have lots of SNARKs which understand this constraint system API and produce SNARK proofs for a particular constraint system. So in particular, we have Groth16, Groth Modular 617, Malin, a lot of polynomial commitments, which are useful independent of SNARKs, as well as these recent inner pairing product arguments, right? Okay. So together, all of these comprise a sort of generic SNARK application framework. So you can use these generic components to develop your SNARK in a very high level. And inside our ecosystem, we've implemented a couple of these applications, such as we have a generic library for proof carrying data, as well as a generic implementation of the zkSystem. And all of these reuse, crucially, the components that we have that live below them. Okay, so let's take a deeper look at each of these components, starting off with the lowest level. So let's see how we achieve the goal there. Okay, so a quick refresher. So today, all SNARKs require at least very efficient finite field arithmetic. Think primes modulo some, integers modulo some prime, right? And they also require efficient polynomial arithmetic over these fields, right? So all SNARKs require this. And additionally, many popular SNARKs, such as which work over elliptic curves, such as Groth16, Malin, Planck, Halo, anything that you can name, really, also require implementations of extension fields and elliptic curves over these fields, right? So all of these things have to be implemented efficiently. So as a reminder, at this level, what we care about is that it should be easy to implement these fields and these curves, right? You don't want to re-implement things again and again, while the performance should match that of a hand-optimized implementation. All right, so let's see how we achieve both of these goals. So starting off with the ease of implementation, right? We show, let's say we want to implement G1 of the BN254 bilinear group. And so let's see how we can do it in less than 60 lines of code. So recall that to specify an elliptic curve, you basically need two constants, this a and b, in the curve equation y squared is equal to x cubed plus ax plus b, right? So this is all that you should need to specify, along with maybe like the generator of the group, right? So on the right, we have our the code for implementing BN254 G1 inside arkworks. And this comprises the three tasks that we have, and this does the three tasks that we want to do, right? So okay, so I won't talk about implementing the underlying fields, but rest assured that it's looks similar to this. It's not very complicated. Next, we want to specify the constants a and b, right? This is what goes in the curve equation. And so there you can see that here a is 0 and b is 3. It's a little bit of an arcane encoding, but you can generate it using a script. And finally, we specify the cofactor and the generators. And this is all you need to do to specify G1. And now this is a fully working implementation of the BN254 G1 and which you can use for your favorite SNARK without worry. Okay. All right. So this extensibility actually allows easy implementations of new curves, and we take advantage of this by implementing inside the arkworks ecosystem many different curves that are used across the ecosystem, across the blockchain space. So, for example, we have the soon what's going to become the industry standard BLS 12381, right, which is used by Zcash, Algorand, and many others. We have BN254, which is still used by Ethereum. We have this Tweedle pair of curves, which is useful for doing recursive composition, which is used by Mina and potentially also by Zcash. We have this family of curves that was introduced in zkSNARK, right, which allows one step of recursive composition, which is used by Celo, used by Alio at the moment. And we also have this M&T cycle of curves. And we also, which is useful for recursive composition. Along with all of these curves, we also have embedded Edwards curves, which might be useful for things like Schnorr signatures or Pedersen hashes. So, for example, we have JubJub for BLS 12381. The nice thing is that for all of these implementations, so for all of these curves, the corresponding implementation looks basically just like this previous slide here. It's just the 60 lines of code. That's all you need to do. All right, and so the reason why it's nice to have all of these curves implemented within the same library is that as interoperability between chains becomes increasingly more important, you don't want to have to rely on multiple different cryptographic libraries in your application, in your interoperability application, right? And so by using arkworks, you could just call one library, and you would have implementations of all the relevant curves that you might care about. Okay, so that's it on the sort of ease of implementation front. What about performance, right? Our goal was to match hand-optimized implementations without doing the hand optimization every time. And so what we actually are able to realize is that our generic implementations from the previous slide match or outperform specialized and hand-coded implementations for each of the curves. All right, so I'll be comparing on the BLS 12381 curve along a few of these metrics, and the baselines will be sort of Bellman, or more correctly, the BLS 12381 crate within the Bellman ecosystem, right? And sort of this is the Rust standard for the BLS 12381 library for the BLS 12381 curve, and it's entirely safe. There's no unsafe anywhere. It's using entirely safe Rust, right? And on the other extreme, we have this very optimized C library called MCL, which uses fancy techniques such as dynamic code generation. And by using these techniques, it's able to achieve very high speeds. So yeah, it's almost, in some cases, 2x faster than BLS 12381, right? So let's see how arkworks libraries stack up against this. So arkworks, with sort of an entirely safe arithmetic backend for the finite field arithmetic, achieves speeds very comparable to the BLS 12381 library, so in Bellman, just a tad bit slower in some cases. And then with an assembly backend for the finite field arithmetic, we're able to get performance that's almost identical. That's much faster than Bellman, and in some cases even beats the MCL library. So for example, for FQ multiplication, yeah, we're faster somehow. Right? So yeah, basically the point of this slide is to show that you can have your very nice implementation from before that fits in 60 lines of code without sacrificing performance. All right. Okay, so that's it on the algebraic front. What about, so let's move on to the next task in the stack, which is SNARK R&D. Right? So here, just to recall, what we care about is good performance, and also that the implementation looks similar to the description of the scheme inside the corresponding paper. Right? So you want to, as I said before, this is important because it allows you to it allows auditors and other readers to be more confident that your implementation matches what is proven secure. Right? Okay, so in this talk, I won't talk about the performance, but yeah, rest assured it matches state-of-the-art performance in other ecosystems, such as in libsnark or in Bellman. And instead, I'll focus a bit more on the implementation matches the math description point. right? Okay, so for this, our example will be the Groth16 verifier, right? On the left-hand side, you have the mathematical description of this algorithm. It consists of these 3 steps, some multiscalar multiplication, a Miller loop, and a final exponentiation. And then on the right-hand side, you have the corresponding implementation in the Groth16 library as it is today, right? So, and it's very easy to see that, which steps match up with, which steps in the code match up with which steps in the math description, right? So it's easy to see that the MSM corresponds to step 1, and the Miller loop corresponds to step 2, and the final exponentiation corresponds to step 3. Right, and so it's slightly less cleaner for other places like the SNARK prover and the setup, but again, it's usually easy to delineate which portions correspond to which steps in the math. Okay, so that's it for this portion of the stack. Let's sort of move up and see how we can write applications that are able to work with these SNARKs, right? Okay, so yeah, to interface with SNARKs, as I said before, we have to do what's called constraint system program. We have to express our high-level problems in the low-level language that the SNARK understands. And because this language is low-level, directly programming in it is quite painful, right? So in particular, many popular systems use this abstraction called R1CS, right? But as anybody who has experience with implementing R1CS-related things, directly programming in R1CS is painful. Even something like a Boolean XOR, it's non-trivial how to optimize that and how to write it cleanly, right? So to resolve this, a number of folks have come up with high-level approaches to programming constraints, so that your program is high-level, but it compiles down to R1CS via a compiler. So for example, with Leo, as you heard in the previous talk. But the issue is that balancing performance inside your R1CS and the ergonomics of having a high-level implementation is tricky. And we'll see a little bit more about this in just a bit, right? Okay, so just to recall, at this level, what we care about is good performance, but ergonomic constraint writing, more importantly. And what I mean by this ergonomic constraint writing is that your constraints should look very similar to native code, right? So it's easy to compare and be assured of the correctness of your constraints. And we also want it to be the case that you don't have to implement common objects again and again, like hash functions or signature verification or comparison, so on. Right? So you want to have a library of common components that you can just use off the shelf. All right, so let's see how we do this. So for the second part, which corresponds to many reusable components, in arkworks, we implement a ton of R1CS gadgets. So we support standard programming constructs such as Booleans, unsigned integers, conditional selection, equality, comparison, and so on, right? Whatever you could really want. But we also support other objects which are more common inside SNARKs, such as finite field gadgets or curve gadgets or pairing gadgets. So you can do all of these inside. We have a very high APIs for all of these, high-level APIs for all of these. And we use these high-level APIs to construct our primitives, such as Pedersen hash functions, the optimized variant from the Zcash folks, commitment schemes, SNARK verifiers, Merkle trees, so on and so forth. So you have all of these implemented, and you can just, in fact, they're all generic, so you can swap out one hash function for another hash function by changing only a couple of lines of code in your implementation. All right, so it's nice to have these, reusable components that you can just glue together, right? But how ergonomic is it really to glue them together, right? That's useless if, I have a hash function gadget, but then to actually use it, it's like take 60 lines of code, right? Okay, so let's assess this by looking at this example of recursive multiplication. This is an algorithm that's used in implementing some finite field-related things. You don't have to know anything about it beyond the fact that it involves some sequence of additions and multiplications, right? So on the top diagram, we have our native code, which is the native implementation of this algorithm. And on the bottom, we have sort of a constraint version of this code, but using an old version of our constraint writing library, right? So this is via some, our old APIs, right? So, and it looks quite messy. It's not clear. It's unclear, like, which portion in the native code corresponds to what in the constraint code, right? And this is also like similar to what you might experience if you were using something like Bellman. So because the API in our old API is inspired very directly from Bellman, right? Okay, so to improve upon this, we completely refactored our constraint writing infrastructure, and as a result, now you can write constraints for this Karatsuba multiplication algorithm, which look almost exactly like the native code, right? So now on the bottom, we have our new constraint, this algorithm using our new constraint writing infrastructure, right? And as you can see, it looks almost identical. Maybe there's a few extra ampersand somewhere, but otherwise there's like no functional difference between the two. And this, as I said before, like helps with auditability, helps with readability, and it's now very easy to see, which parts of the native code correspond to which parts in the constraint writing code, in the constraint code. All right. Okay, so far, so that wraps up the discussion of the constraint writing portion, right? So far, we've done like a very whirlwind tour of the various components in the arkworks stack, right? But the claim I made earlier was that arkworks is like a coherent and modular ecosystem where you can swap out one module for another and have things just work, right? But I haven't yet demonstrated that claim or demonstrated any evidence for that claim. All right, so let's see how we can how modular the ecosystem is by looking at one use case, which is, let's say you've implemented a SNARK-based application, right? And now you want to upgrade some aspects of that application, right? So let's say you want to upgrade the elliptic curve that your SNARK uses, or you want to upgrade your SNARK entirely. So let's see how this can be done in our ecosystem. Okay, so let's say you want to switch between curves, right? And you're using the Grot16 SNARK. To switch between the curves, all you need to do is change exactly one type parameter of your SNARK, and now you will have Grot16 using, for example, the new BW6 curve. And nothing else changes. Everything, the rest of your infrastructure can continue to work generically. And this is the only change you need to make in your code, right? Okay, so let's say I've done this, right? But then I hear of these newfangled SNARKs which have the universal trusted setup, right? So I don't like the circuit-specific trusted setup of Grot16, and I want to upgrade to these new SNARKs. So how would you do this, right? Again, it's a matter of changing just one or a few characters in your program. So you can just switch out this proof system, and now you have now you have an application that uses the Marlin SNARK instead of Grot16, right? And again, that's it. So now you've successfully switched between proof systems, right? Okay, so I've heard of these universal trusted setup SNARKs, but then I hear, oh, there's these new SNARKs which have transparent setup, which is even better, right? So how would I move to that? Well, in our polycommit library, as I mentioned earlier, we have lots of polynomial commitments, including ones which require only transparent setup. And switching between these polynomial commitments for the Marlin SNARK is, again, a matter of changing just one type parameter. And now you've upgraded from trusted setup to transparent setup, almost for free, right? Okay, so I hope this slide illustrates the modularity of the ecosystem. We also have other cases, like, for example, you can switch out hash functions easily. So let's say you develop your circuit initially in mind with the with the Pedersen hash, right? But then we are saying, okay, Poseidon is maybe good enough. It has good enough collision resistance. You can switch it out. You can switch out your Pedersen hash to Poseidon. Again, we're just changing a couple of type parameters somewhere in your program. And then now your circuit uses the much more efficient Poseidon hash function. Right? So basically, the entire ecosystem is built up in this very modular way that allows upgrading components in an easy manner. All right, so that was all about arkworks. How do we compare against other libraries for SNARKs in Rust? Right. So I'll be talking separately about the front end and the back end. By front end, I mean libraries or languages that are concerned primarily with constructing constraints, right? And these fall basically into two camps. So you have either you have sort of a library which does constraint programming, or you have an entirely new language with an associated compiler, right? So the typical example, the prototypical archetypal best example of libraries is Bellman, right? Sort of the original player in this space, and yeah, it supports a lot of. So it supports, for example, for efficiency, it supports non-determinism, right? But as you saw earlier, when you're writing constraints using the Bellman API, it's not particularly close to native code at all, right? It looks quite different, right? So people have come up with these languages which compile down to constraints, such as Zinc or Zocrates, right? And they do look like native code, but they give up on some efficiency requirements, such as non-determinism, right? It's difficult to express non-determinism in these languages. And I'm sure as a result, there's like other optimizations that might be missed because you don't have this flexibility, right? But what we try to do is, as I showed, we try to implement a very high-level API, which supports, which looks like native code, but also allows you to drop down and leverage low-level knobs such as non-determinism to improve the efficiency of your code. So we support this in our library. Okay, so that's it on the front end. On the back end, yeah, so on our front, in our library, we support a lot of curves. As you saw earlier, we have basically all the curves that are used in the ecosystem, as well as a number of proof systems that you can use to implement, that you can use inside your application, right? And this is much higher than what's in the ecosystem, in the rest of the space right now, right? So the nice thing about the separation is that you can mix and match. So you can use any one of you can use our backends along with one of the front ends. And this is exactly what Zocrates is actually doing. So Zocrates is, for example, using, they have a backend which uses an old version of our code, back when it was still, I guess, called zkSNARK. And they use it to implement Groth-Mahler 17 support inside the library. And the nice thing is that when they want to add support, for example, for something like Marlin, they would just have to add maybe a couple of lines of code in their code base, and they could take advantage of our Marlin implementation for free, right? Okay, so I guess to wrap up, in this talk I presented arkworks, right, which is a sequence of libraries for working with all levels in SNARK development, right? So you have algebraic objects, SNARKs themselves, constraints for the SNARKs, as well as applications built atop these SNARKs. And all of this was done thanks to a lot of hard work from arkworks contributors at Berkeley, as well as contributors in the community. And both of these have provided lots of improvements to the ecosystem. And if you want to join, there's always a lot of work to be done, right? So for example, we're looking into integration with WebAssembly. We want to implement new curves. So for example, today, I think Zcash announced a new cycle of curves. So you could participate in implementing that in the ecosystem. And for example, the Tweedle curves were just recently implemented by a first-time contributor to the library. So it's very easy to get involved. If you're focusing more on constraint writing, then again, we have always a need for that. There's always a need for documentation. But there's a lot of stuff to be done in the ecosystem to get involved. We have a lot of support. So we have PR templates, CI, which can catch your mistakes. We, all of us are happy to mentor newcomers. And so yeah, if you want to get involved, you can go to the arkworks to this website, and that takes you to the list of repos. You can also ping me at Berkeley at my email address. And yeah, I guess that's it. Thanks, everyone. Happy to be here.
Very good. I'll clap for everyone. So let's ask, there's actually quite a few questions in the chat already. So let's go back to the top. Or this isn't a question, but it's a comment. Dara mentioned that Halo, asking if Halo comes under RIP, RIPP.
So I guess Halo does not, we don't have an implementation of Halo, but yeah, so RIP does include implementations of inner product related things. There's actually a side to the duplication. So the inner product argument that we have implemented in polycommit does not use RIP yet, but we're trying to reduce the duplication. Yeah, and eventually we do plan to support or extend our PCD library to support accumulation-based recursion also, hopefully in the near future.
Your mic is just brushing up against your
okay.
sweater a little bit.
I'll just hold it.
Cool. Okay, Rob asked, what factors went into the choice of traits versus macros on API?
So I mean, I don't think there's a need for separation. So you can still combine traits and macros. We just haven't written our macros. But what traits allow you to do is to write code against a generic interface. So I can have, for example, a generic curve interface and just write my SNARK code in terms of that, instead of having to hard code inside my SNARK implementation a particular curve. So what macros allow you to do is to sort of deduplicate some common code And what traits allow you to do is to have a common interface. So they sort of serve as orthogonal tasks in this world. But yeah, there's certainly like you can combine the two to leverage the deduplication that macros provide and still have the common API that traits provide. We just haven't gotten there yet.
Rob has a follow-up on execution. Which components can target a no STD WASM embedded environment? What are the major barriers if that is not supported? And I think there were some answers later on in the chat, but maybe you want to say something on that.
Yeah, that's a good question. Yeah, so basically we develop all of our libraries to support, I guess, no standard with allocation. So you can use it in WASM as is already.
Kev asked, can you comment on audit availability or auditability of the code?
Yeah, so we do try to have a good documentation and good comments everywhere. And as I said, we try to make our code sort of match the description in whatever paper is available. And I believe there's been some audits for parts of the prior versions of the libraries, of some libraries at various points in time. But I think overall it's fairly, we have enough comments to make auditing relatively easy. We also have good tests for some parts.
Dara, I was asking, do the curve APIs inside the SNARK support both complete and incomplete formula? Formulea. Oh, that's plural.
Right, so that's a good question. We've actually been looking in, so currently so a prior version had only incomplete formulae. And since then, that required some hacks to work around for scalar multiplication. We moved to supporting only complete formulae. But now for scalar, for sort of like addition and doubling, we use only complete formulae. But we want to upgrade scalar multiplication to use incomplete formulae to take advantage of the speed and the efficiency improvements that provides. So
Derek
yeah.
had another. Oh,
no, go ahead.
Do you want to finish? Derek had another one. I noticed there were no names for constraints in the new API. Is there any compromise on debuggability here?
Right. So what we do now is instead, the sort of in the Bellman approach and like the old arkworks approach, you had to specify for each constraint a particular name, and that does allow like allow you to give human-friendly names for each constraint when you're debugging or profiling. So what we've done instead is try to use existing infrastructure called tracing, which basically, whenever there's a new constraint, it like takes a snapshot of the function name, line number, and so on. And so it gives you exactly where the constraint was generated and like what the path to the constraint was. So you can know which constraint is failing and what the cost of each of the overall constraint system, how they're distributed. But it needs a little bit more work. It's definitely in an early stage there, but I think it's the future.
Isaac asked about WASM support. If you could speak a bit more about that.
Yeah, so WASM support, as I said, like we already have no standard and Bellman, no standard implemented. So all of our libraries support compiling to WASM. It's just a question of sort of writing the integration with JavaScript and maybe writing out a nice tutorial that leverages this compiled library. Our library is compiled to WASM, which I'm like absolutely no experience with web-related things, so I wouldn't know how to do that. But yeah, so like from I guess the arkworks side, compiling to WASM, we support that.
He also asked, also with Rayon.
Yeah, so I think there's an issue somewhere which shows how to replace the Rayon thread pool with something related to web workers, I believe. So I think that should work for multi-threading in WASM.
I'm curious if there are any more questions. The chat in here is interesting in general. Pratyush, you should totally read back because there's like conversation happening, people answering questions. But yeah, if you do have any more questions, please put them in the chat now, because otherwise we will sign off. And it seems like I think maybe questions are answered. Either way, you should stick around because I'm going to be doing a concluding talk and also pointing us at the after party. So don't leave the site yet. But yeah, if there are any other questions, please do put them in the chat for Pratyush. You're just getting a lot of clap. Maurizio asked, is zkSNARK gone then?
So zkSNARK, I guess, was the old name for this ecosystem. We decided to move away from it because it was maybe too closely associated to the paper. And since then, there's been a lot of contributions from folks working on other projects and things completely unrelated to zkSNARK. And I feel like sort of the primary value of the ecosystem is not in like the zkSNARK specific parts, but rather in everything else, in everything below that. So zkSNARK, I guess, is deprecated as a name for the ecosystem. But like a lot of the code just lives on, just refactored and moved around and better documented.
That's actually good to know. What's the parallel scalability?
So, okay, that's a very broad question, but I guess so we parallelize both FFTs and MSMs using, basically whenever there's an opportunity for parallelization, we try to leverage it using Rayon. So FFTs, MSMs, batch inversions, wherever we can, we try to parallelize if it makes sense.
Cool. All right, well, I think on that note, we can wrap up. So thank you so much for the talk, Pratyush.
Thank you so
to
much.
Everyone who listened and asked all these great questions. This was fantastic.
Yeah, thank you so much, Anna, for having me. And thank you, everyone, for asking the wonderful questions.